So one of the problems, or one of the challenges with understanding Coulomb's law, is that most matter is electrically neutral, has as many plus charges as negative charges, and that means that it's hard to see Coulomb's law in action. We can separate charge. We can't create charge. Charge is one of those things that's conserved, but you can separate charge, and usually that's done by rubbing two different surfaces. I'm just going to tell a story that some of you may appreciate, but when I was in my probably middle school years, my mom would take me clothes shopping at the start of school, it seemed, which was always a painful experience for me. But there was one store where we would go to buy my school clothes, and this store, somehow their carpeting was made of a material that I realized after a couple of trips that if I wore leather shoes and I shuffled my feet across the carpeting, I would acquire such a large charge that if I went to touch anything metal like a doorknob, a spark would jump out from my fingertip 2 to 3 inches long, and it hurt. It hurt, but it was so cool I kept doing it. So I don't know what happened at that store, but the point is that when two dissimilar surfaces rub, frequently one material is more electropositive than the other. Don't confuse that with electronegativity, which you're going to see in a few months perhaps, or weeks, but electrons will be transferred. So we can create charge. And I'm going to do that now. This is a little toy that I bought for my daughter when she was about 3 or 4 years old at a science museum, and it's called a fun fly stick, but it's a miniature Van de Graaff generator, and when I push the button here, maybe you can hear there's a motor running. There's a belt inside here that rubs against a brush and will actually deposit extra electrons on this cardboard tube. Where are those electrons coming from? And they're actually coming from my body. And ultimately from the ground, so I'm going to acquire a little bit of a positive charge. And if I push the button and hold it steady, you can see the negative charge accumulating on the tube. No, I'm only kidding. You can't see charge. So how would we know if there is any charge on there? And I'll need to have something else that's charged. And I just happen to have in here a little piece of mylar. And you can see it's quite light. If I let it go, it falls due to gravity. It's being pulled down, but not very quickly. But if I touch this to my generator, you can see it's not only does it kind of poof out a little bit, but it also stops falling. And they can actually repel each other. And I can try to do one more thing to show you that I am positively charged, is I can kind of get this to bounce back and forth between my hand and the stick. So there's a little example of where it charges, and let's see if we can do a few calculations using Coulomb's law. So if I now take my rod, my fun fly stick, which is negatively charged, and I've got my, pardon my lack of any artistic talent here, my flyer here, and it's also negatively charged after it touches. You might have noticed it had to touch to transfer some charge. And let's say it hovers at some distance d. If this is hovering without moving, then I know the force acting on it is 0. But there are actually two forces on it. There's the weight, which is pulling it downward, and then there's the electrostatic force, which is pushing it upward, the electrical force. And if those two, if the net force is 0 newtons, then those two are equal. So I can immediately write, well, that, let me put in some numbers here. The expression for weight is the mass times the acceleration due to gravity. And for us, the mass of these happens to be about 0.2 grams, and I better express it in kilograms, and please, there's a special place in AP Chem Hell for students who ignore differences in units. So 0.2 grams is not the same as 0.2 kilograms. I'm going to rate that as 0.0002 kilograms. You'll learn that a joule and a kilojoule are very, very different things. And then for G, I'm going to use 10 meters per second squared. The actual value is 9.8 or close to 9.8, but we can round to 1 sig fig. And that means the weight of this object is going to be 0.000 or 0.002 newtons. And I'm going to set that equal to the electrical force. So I get weight equals electrical force, or 0.002 newtons, equals K times Q1 times Q2, that's a terrible Q, over D squared. And now I know the value for K. I'll remind you it's about 9.1 times 10 to the 9th, using Newton meters squared per Coulomb squared. And I could estimate the value for D. And I'm going to guess that D was about 10 centimeters, or a better way of expressing that would be, I hope you all said 0.1 meters, because I got meters here. And then I should be able to solve for Q1, for the product Q1, Q2. I can't really tell what they are separately, but one good approximation I could make here is that Q1 is approximately equal to Q2, and that means I could replace this by Q squared. I'm going to stop there and ask you to go ahead and figure out what the charge might be on our little flyer here. And then as chemists, we'll be concerned not only with what the charge on the total flyer might be, but if we know the charge on a single electron, how many extra electrons has it picked up, and how many moles of electrons. Because we're in chemistry, we really care mostly about moles. It's very hard to count billions and trillions of individual particles, so we really prefer to talk about moles. And I'll see you in person or on screen shortly, and we'll work on this. So thank you for watching, and good luck.